Okay. Right, starting again. Welcome back to computational physics. Today we'll talk about MC, Monte Carlo Markov chains. And you can still reach me either over the phone, but preferably over email if you need help with your Jupyter notebooks. We do have a text. It's not quite required, but it is useful. And so please have a look at the Python for astronomers, which is probably useful for physicists as well. OK, so last week we talked about Kolmogorov-Smirnov and AD test, Anderson-Darling test. We talked about bootstrapping and jackknifing and what fit to use. So the bootstrapping and jackknifing are ways to subsample your data, or resample your data. And the Monte Carlo Markov chain is essentially an expansion of that idea. So we talked about when we did the chi-square fit with the slope and the intercept that we're just going to sample parameter space either this way or that way using slope or intercept. And we have to go and use every combination of slope and intercept and find the chi-square and then find the lowest value in that array of values. But what happens if you have non-Gaussian data and if you want a posterior distribution? So we're going to talk about a technique called Monte Carlo Markov chains. And so that's a natural progression from bootstrapping, from jackknifing, from how do I go through chi-square, how do I go through parameters, the chi-square parameter space. We talked about inferring causation from correlation. Ooh, it's Halloween. So no, we should never do that. But we do want to know how we infer values from model values from our data. How do I get there? And so we can use that with bootstrapping and jackknifing. Those are the two that I talked about last week. You can subsample and then try it again. And then I can, but I do assume a Gaussian distribution of with a mean and a standard deviation, because that is what I'm assuming is true. And if I want to get to those, I can subsample my data and use that to infer the Gaussian distribution assumed uncertainty ranges on my inferred values, right? So I subsample my data, I fit my models, and then I get a distribution of values for which I take the mean and the standard deviation, and that gives me the uncertainties. But the underlying assumption is that the mean and the standard deviation are a good description of the confidence level for the inferred parameters. OK. So which fit to use? Got data? No. Go get data. Got data. So we're always here. Does it have errors? No. Do you care? That's an important one, right? So if you don't care, you can always do a linear regression. There's your slope and intercept. And you go, good enough for me. Off I go. Or I just want to compare it to two samples against each other. I'm not interested in their uncertainties that much. I'm not interested in the confidence levels because I've got I get a p-value anyway. So I know how confident I can be in these comparisons. Or if I do, I bootstrap or jackknife. But the underlying assumption is that it is a Gaussian distribution for the inferred parameters. If I have good errors, they're Gaussian, I can do a chi-square fit. That's fine, and I'm good. And if it's not that many parameters, this is well-behaved data and not that many parameters, I can just step through the likely ranges and get a good fit. And the chi-square tells me how good that fit is. If that's not the case, if the errors are no longer Gaussian, if the distribution in uncertainties is no longer Gaussian, if there's what looks like there is something going on where you have an additional parameter driving your data, and if there's essentially shenanigans going on. So you can fit a maximum likelihood fit to that. But then do you need errors on that? Then MCMC is your new friend. Because essentially, it's the same as a chi-square fit, but it's no longer assuming Gaussian errors. It's no longer taking that initial assumption that your end result has to be a mean value with a Gaussian around it. So here's Gaussian noise, and if we don't have Gaussian noise anymore, so that's like the nuisance parameter, so there's something else happening, there's just a disproportionate number of extremes going one way, for example, or there's some other shenanigans, then we are beyond Gaussian territory. And I think assuming Gaussian noise is so often true for simple experiments especially that it becomes a habit thinking that all remaining noise is always Gaussian. It always looks like this distribution. That is good enough. We can go with that. The thing is, we are going into complex physics. We are going to go into complex models, and that need not be true. And in fact, that is an interesting prior for your science, assuming that it's Gaussian. Because not Gaussian doesn't mean not random. It just doesn't. It means it's not a Gaussian distribution. So never tell me the odds. Actually, no, please do tell me the odds, because I would like to know what my posterior distribution looks like, and if I assumed Gaussian and I shouldn't have, that is good information. This also hooks into what kind of unknowns do we have? We have the known values, we have the data, and we have the known unknowns, the things we're after, the inferred parameter, our model, right? So those are the things, in an ideal world, that's the end of the list, right? We have our data and we have our model that envelops all the relevant pieces of information, and then we are going to fit our model to the data, and we infer our information. We infer our parameters. Those inferred parameters we've got a measurement for, and we've got uncertainties on, and we're all good. Problem is, we have unknown unknowns. And there is a famous quote from Donald Rumsfeld: there are known knowns, there are things we know, and we also know there are known unknowns. That is to say, there are some things we do not know, but we're aware of them. But there are also unknown unknowns, the ones that we don't know, And if you're in a complex situation, which this gentleman was dealing with, you do end up with things that are unknown unknowns. Literally something that you weren't even aware you were unaware of. And so we essentially have four kinds of pieces of the puzzle. If it's a little more rigorous, we say we have data and constants. These are things we know, and these are known knowns. The data we've got, the constants, physical constants, for example, we don't need to have a sliding scale on. Then we have the known unknowns, the model parameters, the things we want to infer. Great. This is typically how we think of physics and physics models. However, we have unknown knowns, so things that everyone knows. Everyone knows that gravity doesn't fluctuate. Everyone knows that the lab doesn't freeze midsummer, right? Some of these things are like, yeah, they're reasonable assumptions, but they can be things like the lab turned into something, the lab never freezes, and then the heat broke, right? So we can have things that are unknown, but we should know about, and biases make their appearance there. So things we all know for sure is always worth examining a little bit closer, because that's where biases happen, not just in the humans that do the analyses, but also in the data itself. Biases can have slipped in one way or another. We're simply not sensitive to the red part of the spectrum, so those things didn't make it in. We're not sensitive to things that are farther away or really, really close by. So there's a range that we weren't aware of but should have been. And then there's the unknown unknowns, things that we were neither aware of nor we understand. So, that's funny. And usually that's how a great discovery story in science starts, right? That's funny, or that's odd, or why is this thing misbehaving, right? So when we find the that's funny story, then it goes into, and then we looked at it closer and we got a Nobel Prize later. Usually, that's funny is followed by, I wonder if it's a bias, I wonder if it's a sensitivity issue, and you go and explore it some more, and it turns out to be an unknown, but something that we know about, or go like, oh yeah, we're not. Oh, there's a red leak in the CCD. All these things where it's like, yeah, Oh no, we're aware of that. It's a bias. It turns out to be a bias. But unknown unknowns is also what we're after in physics, or at least in discovery. So how do we compare these things? How do we find them? And Monte Carlo Markov chains is a new technique to use to actually sidestep a few things. So Gaussian error is an assumption, easily leading to a bias. You can underestimate your errors if you assume that they're symmetric. They're not. They don't need to be. There could be like smaller error on one side, much larger error on the other. But the preferred value could be doesn't need to be smack in the center. How to explore multidimensional parameter space effectively? This is a problem every time. Unless your model has one parameter, actually, unless your model has 0 parameters, you always have multiple dimensions, you always have multiple options, and then you have to explore every combination of, say, slope and intercept, or slope, intercept, and range. And so you have to jump through all of this giant parameter space. How do you do that quickly? How do you do it efficiently? And so how to spot degeneracies? Where is the point where if I increase one parameter, I have to decrease the other in order to to keep the fit correct, right? So if the two of them know about each other and you have to change both in order to keep the fit equally good, that means they're degenerate. Degenerate space, degenerate model space, degenerate parameter space is not a bad thing. It's just something that you need to be aware of. And how to compare multiple models to each other. As soon as I have a model with 2 parameters, or let's say I have a model with 3 parameters and a model with 4 parameters, how do I compare against each other? How do they perform? Right? A single value won't, even a reduced chi-squared is assuming Gaussian noise and assuming that all parameters are not degenerate. So how can I compare them easily? How to compare completely different measurements of the same values, right? So I can have completely different techniques modeling the same data. And so I have an example of that later. All right, so first things that goes in is the priors. What part of parameter space are we going to look at? That is a prior. You decided that before you even fit a single thing. So this is a reasonable range to do this over. Is a prior, this is an expectation that you're building in. Do not assume that you will never have assumptions going into a fit. In fact, just specifically state them. Say, this is the part of parameter space that's reasonable. That is my prior. And you can start with putting as wide as possible, saying like, I don't want unphysical things. So things like below 0 Kelvin. Please, Mr. Computer, do not spend any time making models where my sun, the sun is below 0 Kelvin. The center of the sun will never be below 0 Kelvin in a good fit of the solar parameters, right? So that is just silly. So let's not go there. Okay, that works. But it is also the place where you can build in unconscious biases, where you go, well, I can't possibly be over there, right? So another example is, well, my lab never freezes. Is always my favorite one. It's like, yeah, and then it did. So it's important to remember that you keep it as wide as possible and keep it as reasonable as possible, but you will build in a prior. That is something that it's better to state this up front. It's better to put your expected range front and center and go, this is what I'm expecting. And in fact, priors can not just be a flat prior. It's like, I think this is much more likely than this, and I have a reasonable assumption for that. Reasonable doing a lot of work here, but it's like, yeah, it drops off. I think it becomes increasingly less likely over there. So putting priors in and explicitly stating what said priors are, like these are the odds going in, I think that's actually very good science. It's not just your hypotheses, but your expectation. So remember fitting a line. Okay, well, we already did that there. We inferred the parameters, slope and intercept. If you loop through all possible values, if we don't loop through all possible values, we do put in a prior. We put in the range that was reasonable. Oh, you know, the points go up, so there has to be a positive slope. So it has to be above 0. I just got rid of infinite negative numbers. That's a prior. It's a very healthy prior. It was a sensible one. We don't need to spend computing time on that because we don't have infinite computing time. So we do need to make a choice. We need to make a choice if we want to figure out what the slope and intercept actually are. And so they're probably somewhere in this range. This is your prior. That is a reasonable prior that I put in before I did my chi-square. And so you have to have one. There has to be some prior. Be aware that it's there. Otherwise, your algorithm has to go through infinite options. It has to go from minus infinity to plus infinity for the slope and minus infinity to plus infinity for the intercept. So that's infinity long times infinity. I don't think I have that amount of computing power. So, and even then with that, there's actually a third parameter. It's like how closely do I step through the parameter space? Do I take huge coarse steps because, you know, I don't need to know it that accurately, or do I take minute steps because I really want to get a close map? And then for each possible slope and intercept, I've computed the chi-squared. So essentially, I end up with a landscape. Remember the chi-squared landscape? The chi-squared landscape is essentially, here's my intercepts, here's my slopes, and I've mapped the height there. The people keep thinking of this as a height, like how high the chi-square is. So we're up to 6,000 here. We're down to 3,000 over here. Okay, so this is where the minimum is, and that's where the happy hills of absolutely terrible fits are. So we got the chi-square landscape, and we just plotted through here linearly, and we spend just as much time as we did on the interesting bit here, where you know, it's going down and there's lower and lower values, as we did into this blank canvas of super high chi-square values. So if I want to know more detail, I can say, well, I'll recompute. And so the initial optimizations were, for example, hey, I'll just take a block here and recompute this in much greater detail. And then take another grid and take it in much more greater detail. But that is computationally heavy. And this is just a slope and an intercept. So there has to be a better way. Well, there is. And so we use random walkers. And this is not what is it, the living dead? But there is a walker. These are walkers that randomly stumble around parameter space, but not quite randomly. So we've got an intercept, we've got a slope, and we start at a position. Maybe the least likelihood, so some optimized fit, right? So it's like, okay, that's where we need to be. Then it starts to randomly walk around. And it starts to randomly walking around mapping the chi-square landscape and going, oh, I'm going up. And if it stays up the same way, I'll start making bigger steps. And I randomly turn and go in a different direction. And especially if I'm like in an interesting bit where there's lots of gradient in the chi-square, I'll just keep walking around. But if I'm far away in relatively high chi-square, I take one step and go right back, or make a turn around and make a big step back. So this way you spend a lot more time in where the chi-square values are low and where there's a big gradient. So it's like, oh, this is the interesting bit, and I don't spend a lot of time on the bit that I wasn't interested in anyway. So you spend your computational coin, so to speak, wisely. Also, note that we didn't have to give a range here. You just start walking around. And unless there was a prior that said, yeah, not below this, you can just start walking around, and you won't spend time far away. You just spend most of your time where the low values are. If you are talking about somewhere with, we'll talk about that in a minute, sorry. The random walkers, pretend they're zombies who follow the rules. So they're randomly walking, and there's different flavors of walker. And so MCMC is almost like a whole family of ways to fit to a complex model, because every time you can employ slightly different Walker models. Random enough to probe the whole space, but the rules ensure good coverage near the optimal value. So it starts taking smaller steps if the chi-square gradient is steep. It starts taking bigger steps if it's just, high chi-squared. And so it goes, oh yeah, this is not the bit that I need to look into in detail, so bigger steps. And then, oh, here's the chi-square gradient is much higher, so I'll float around here randomly. So the walkers are incredibly useful for this, to map the part of chi-square space where you need to be. So here's an example where you have two values that you're trying to fit, and it starts at a random spot. Doesn't matter where that is, because it goes, nope, here's, keep walking randomly, take bigger steps occasionally to see if there's anywhere like the chi-square doesn't get any better. And here I'm like, oh, look, there's gradient. There's gradient in the chi-square, lots of gradient, and I need to be, and as soon as I go like, oh, the gradient goes back up, go back, it goes back out here and goes, no, I need to be over here somewhere. So the rules essentially start mapping the gradient in chi-square space and sticks within an area which we want to map. And so all the chi-square values of the Walker afterwards give us a probability function. This is like how good the fit was. You can think of it as like the inverse of the 1 over chi-squared, for example. So the 1 over chi-squared is really great here. So this is the best fit. And here's the optimal fit. So about here is good. But note that the actual range where the values of the Walker are is not symmetric, and this is the probability, the posterior probability function. So really, this is my probability of good fit, and so the error bars kind of start here. This is the best value, and then end here. They're asymmetric. This is not a Gaussian, and if I try to approximate it with a Gaussian, it doesn't really do a great job. So I can see whether or not these parameters, they're not that degenerate, but they are definitely giving me non-Gaussian posterior distributions, probability distributions, and error bars that I can say like, well, 14% of my steps were here, 84 of my steps were here, and so this is my 2 sigma or 1 sigma confidence range, and this is where my value should be. So you get asymmetric error bars. Another example, as you step through here, steps, it goes up, nope. So bigger steps, gets stuck a little bit into a local minimum, but because it's random stepping through, it kind of gets back out and goes, oh, hey, no, and it makes it out of the local minimum and then finds the actual minimum and starts exploring that. So the fact that you do need to burn time, you need to burn in, as this is called, so you need to step often enough to probe this sufficiently. So these are qualitative steps, but essentially you need to have a point where it's like, yeah, I got a pretty continuous idea of how this distribution looks like. So this takes computational time still. Having lots of walkers do this takes time. There's the burn time, the burn-in time is the trick for MCMC. However, the neat part is that you can have more than one walker. Have a bunch of zombies float around your parameter space and actually sample everything, and then you can sum them all together and you get these. So this is great if you want to have multiple core computers. Oh, hey, we have those now. So instead of having one CPU just diligently step through all of this blank space that we're not interested in anyway, it will this walker can start here, this walker can start here, and they'll all find this, and so their eventual distribution will look like that. So you don't even have to have one walker. You can have multiple walkers. You can have hundreds of walkers. Can I just pump up my my error bars and just say, oh, there's my error? It's like I'll just make the biggest one, like whichever side was the biggest one, that's my standard deviation. So here's my mean, that's my standard deviation. Here, back to Gaussian, terminology. No, if you overestimate on one side and you still underestimate on another, this is bad science. That's not the confidence interval that we're at. Also, the limits on one side will be constraining. It will help with constraining models, with constraining theory. So you are actually misleading your audience here. So don't do that. And it is super easy to intercompare once you've actually mapped chi-square space like this. So, oh, suddenly we're no longer using 2 inferred parameters. We've got 1, 2, 3, 4, 5. Okay, how does that look like? Well, this is what we call a corner plot, as you can see. So the corner plots plot all the variables against all the other variables, so you can see where their how their chi-square landscape looks like. So where all the walkers ended up spending their time. So they spend a lot more time here than they did there. So I'm seeing, time spent by the walkers for 2 models, and I've noticed that this one's a little amoeba shape, and this is actually pretty well described by Gaussians, right? So this one's these 2 are pretty independent for the red model, but the red model is fairly unconstrained compared to the black model, but the black model is a little degenerate. But if I look at the posterior distributions, which are over here, they look fairly Gaussian. But if I'm looking at both parameters against each other, I can identify where they're degenerate. These 2 are degenerate. Look, if I slide one down, I have to slide the other one down in order to stay in the same chi-square. This one is incredibly, this is very well constrained in one and quite free in the other. So these are the kind of things where I can now compare both models. And if I put both models on top of each other and say, oh, well, if I do the constraint by both techniques on the same model, I can say, actually, I'm starting to get pretty confident we're going to be in here. Like, I'm starting to get pretty confident we have to be in this range here. And so if you can combine one model that's not great in measuring one value and another one that's great at it, and then combine them and actually get the sum of the 2 different techniques that are both trying to measure the same underlying inferred parameter, will end up, the sum of them will be much more accurate. But that's by summing these areas together. Hey, does this have anything to do with this word Bayesian that I keep hearing? Yes. So Bayesian is a kind of statistics where you say, my prior assumption is X. I am going to assume that there's a 4% chance of rain, and then I'm going to take a measurement. I'm going to step outside and see if it's raining. And so every new measurement, every time I step outside and go like, no rain, yes rain, improves my expectations for the next. So it's kind of like how those walkers went, right? So if I start and I just do a few, it will have a posterior distribution, but every time I do, I get closer and closer and closer and closer and closer to the actual probability function that it's raining or not, right? That's a yes-no question, but you can have a continuous path as well. And so continued iteration actually approximates what the real values are as I go along. But I started at some point, right? And so that can be a prior starting point. That can be my priors. So the idea in statistics, Bayesian statistics, is like you always have a prior and you update your expectation as new data comes in. So these are the posterior probability distributions. So that's actually the thing that the walkers are sampling. It is the thing that we also get out, and that is, here's your probability distribution. You had an initial value, but here's the actual distribution that you get afterwards. That links well to the actual language of science, right? So we talk about things which is fairly Gaussian, which is this is the mean, or this is the best value, and we think of those 2 as the same, and it's not, right? So this is where the best value is, and here's our confidence level. And that confidence level we think of as in 1 sigma, 2 sigma, 3 sigma, so 68% chance, 95% chance, and 99.7, not 100%, but 99.7 lies within 3 sigma error bar of the measurement. However, if we want to do that, we can just say our 1 sigma confidence level is where we find 68% of the walkers all the time. So here that is pretty close to Gaussian. But if we get something which is not, you can still say this is my optimal value, but I have, I find 68% in this, wide range. And so you can still say what your plus or minus 1 sigma error bars are. But they are now can be asymmetric, right? They can be, 1 sigma is only a little bit away from my optimal value, but the 1 sigma to the plus side can be, much further. I like the fact that you can also do that with language. So objective distribution, pretty good in the center, okay and good on either side, and then awesome and junk. And then how that changes with culture, which culture you grew up in. If you're an American, everything, as soon as you're above this place, it's all awesome, like the Lego movie, or Eastern Europeans, where everything is terrible, even if you're a sigma or 2 above the mean. So growing up in Europe, I would say that we're closer to this, to this. But that's also true in science, right? So there's actually what people say is high confidence. Is like, what percentage levels are you actually talking about? People, sociologists have actually done studies to see what people mean when they say significant. Where exactly does that lie? And so it's funny how that works. But in science, we actually have very strict standards for that, which is, it has to be at least 1 sigma and then preferably 3 sigma until we actually say what our confidence levels are. Instead of Gauss, you can also use the student T distribution. I don't use it very often, but you can, people compare that instead of the Gaussian distribution. You say, like, yeah, compared it to the student T distribution, which actually has slightly, I think it actually is a little steeper at the end. It doesn't have as much of a wing as the Gaussian. So let's take a real-world example of MCMC. How did we step through a complex model and sparse data? So the models can be complex and degenerate. Keep that in mind. Even if we think that this model parameter cannot possibly have know anything about the other one, there is absolutely no law requiring that your physical model needs to be a degenerate, needs to be an orthogonal parameter space. In fact, most likely it will not be. So even the simplest one, the fit the line, was degenerate, right? You can get equally good fits with a slightly different slope and a slightly different intercept. So, and the data is sparse. Your data is never infinite. Your data always samples whatever you're looking at. So it covers the desired parameter space. And that last part is important. If your data doesn't even go that far or go that far out or covers the bit that you're interested in, there you go. Then MCMC can't rescue you. So our example is, well, let's fit the shape of the Milky Way, the entire galaxy, using just 274 stars that we found in Hubble data. And these are special stars. They're called M-dwarfs. And so they are rare. Well, they're not rare, but they're small. And so they're hard to see because they're faint. And so we only pick them up at any kind of distance accidentally in a Hubble picture. And this was published in Van Vletter et al. 2016, which is Van der Vlucht and Van Vletter are two students of mine for their BSc project decided to do this with me. And so what we're looking at is a Hubble picture in a couple of colors, and we're looking at these odd, you can occasionally see here's a star, there's a star, here's one, there's another. You can pick the stars out because they have a little bit of a cross shape. And so you can identify the stars in each Hubble picture. And an individual Hubble picture will give you, 5 stars. That's not a great number of stars to model the whole galaxy that is comprised of billions of stars out of. So how do you do that, right? So this is sparsely sampling the whole Milky Way. Well, there's a few things. One, here's the whole Milky Way. Here's the disk of the Milky Way. There's the bulge. So we're in a disk, and there's like this halo of stars around it. And counting stars and trying to figure out what the shape of the Milky Way is something that we've done in astronomy for a very long time. And we've done it I think Herschel in 1758 had his first model of the Milky Way based on star counts that he did by observing in all directions. It is also the one that we got wrong so many times because, again, we brought our biases, we brought our priors, we forgot about unknown unknowns. So it is the thing that is traditional and done badly often. So what do? Well, instead of trying to map the whole Milky Way, we just randomly sampled here at the green blobs everywhere. We found these M dwarfs in every little HST in the Hubble images and counted how much we got. And we only get from 0 to 5. So there's not a lot of them, but with we get this many here, this many here. The Hubble pictures are different depth. So we have sparsely sampled our Milky Way, very sparsely. And now we're going to fit a model to it. We have two parts of the model. One, this is the disk, and this is the stellar halo. Our assumption, or our prior, I would say, is that we have a disk, and there is and the halo, and they look like this. We base that on scientific literature. This is what other people have posited as a good shape for a galaxy disk and a good shape for a halo. So what we have here is the density of stars at the polar coordinates, right? So polar coordinates means that we got a radius and we got a height above the disk and a height below the disk. It's symmetric. The disk is symmetric. So polar coordinates will do. And so we got the density in the center and an exponential drop-off with a radius from the center with a certain scale. And then the vertical profile is a secans hyperbolicus squared. For how far above or below the plane are with the typical scale. This is mostly for historical reasons because that turned out to be a parameter that worked pretty well, so this way we can compare to previous results. And then we have the halo. The halo density is the density here at around our sun. The fraction of those that are in the halo belong to the halo, and then we've got the radius again from the center, and the radius and height of the sun, right? This dot, O dot, is the sun, the symbol for the sun. So we have a position where the sun is and how far above the plane it is, and then we have where the stars are in radius and above the plane again, and we have the K, which is the flattening of the halo, and the power law of how the halo drops off. So what is what? Well, we have data. We measure a star at a position with which we can translate into radius and height above the plane. And so we have data points, and then we have knowns. We have the position of our sun in the Milky Way. That's something that other people have measured. So it's like, okay, those are constants. And then we have unknowns, which are the orange ones, right? So we don't know what the density of M dwarfs in the center is. We don't know how they drop off with radius. We don't know how they drop off with height above the plane. We don't know what the parameters for the halo are, and we don't know what the fraction of stars in the halo are, a fraction of those stars in the M dwarfs in the halo are. So this is something that we can measure from local, and so we take that from the literature. We have a fair number of unknowns. How many of those can I actually measure from my sparsely sampled data? Now here comes the trick. Here's the actual final result, but I'll take you through how we got there. So we have the P, the K, which the K is the flattening of the halo, the P is the radial drop-off, the Z is of the disk is the thickness of the disk, and then F is essentially how crummy the data, how good the data are, well the data are following the model. Here's the thing that I want you to notice. In our corner plot, we have posterior distributions. Not all of them are reasonably Gaussian. There are some that have a tail here on this side, or they look much more constrained here, but they still have a tail. We can also note that some of them seem to be much more degenerate than others, right? So we can actually see some degeneracies. But all the walkers do seem to prefer, being at the values that we found. Okay, so we can do model comparison. We have multiple parameter models, a lot of parameters. We have non-Gaussian uncertainties. We have sparsely sampled data. The nuisance or random parameters, which one of those can we set to something, and do we have degeneracies? Yes, we can see some. How to compare them from model to model. Different parameters left free or fixed to something that we found from the literature. First, simpler model. Let's not invoke a halo at all. So let's drop all the halo stuff and just say, they're all in a disk. That doesn't seem to work very well. The walkers just spend most of their time just wandering around randomly, not fitting the data terribly well at any given point. Okay, I add a halo. Suddenly, everything snaps into position, and the walkers spend way more time circling what looks like a better fit. But I did add a bunch of parameters, so my model became a lot more complex. But I can compare the two, because this doesn't work, and this one seems to work much better, although there are some degeneracies. Okay, well, I can fix the fraction of stars that is in the halo. Let's just say that the halo is, by definition, 10% of the Milky Way, and then I can just see how that works. Well, here we are really working with an artifact here. Like, this is far too spiky, and there are some degeneracies. So I don't like this one so much. I can fix the scale length. Actually, this is better. The scale length we know pretty well, so that's in the disk. And so let's fix that and see if we can at least constrain the rest. That's the one that we ended up with. But we can also say, well, let's fix the slope of the stellar halo. Let's not try to measure that. No, this is worse, right? These are artifacts. And I can immediately see that this has some weird artifact. Oh, and this ones seem to be much better, like they are good, much more random around the value that we're interested in. There are some degeneracies, but we've minimized them. And I can say, well, let's fix the central density to something that we think is reasonable, but no, that breaks everywhere. So you can see where, you have an instant intuition of whether or not your model is doing well or not. So, cool result. We got a vertical scale for the Milky Way that is 300 parsecs across. That was something we didn't know. Then we can infer from the whole model, by summing the whole thing together, that there are 58 billion, correct with a B, M-dwarfs in our Milky Way. From this 274 to 58 billion. That's 10 to the 8 orders. That's 8 orders of magnitude difference. So talk about sparsely sampled. We infer 8 orders of magnitude more. And you can do that because you can infer which models worked, and then you can take that step. Now, this is fairly uncertain, but we got a value out of it. And 7% of those, that's the fraction in the halo, is in the halo, and that's something that we were after, right? So we were after this is a cosmological model that says that's the fraction of stars we expect in the halo for a typical Milky Way kind of galaxy. And look, there we are. But not only that, we have an error bar on that, and that error bar is asymmetric because it's not completely independent from other parameters. So we got a confidence level, and that confidence level puts us right on where we expect this thing to be, and also seems to be in agreement, because this is in reasonable agreement with a previous value from the literature. So this is amazing. And so, yeah, this was immediately published in 2016, goes around the world. There's a wonderful, students count 58 billion stars. No, they didn't. They inferred 58 billion stars. Much easier. So it shows you how powerful MCMC can be. You have sparsely set data. You don't quite know which models you want to use, which parameters you want to set, you want to fix, and you can see a posterior distribution straight off from all the walkers. So very, very powerful, good for the kind of thing that you really do get in astronomy and physics, which is non-Gaussian, sparsely sampled data, and you need posterior distributions, not the assume it's Gaussian all the time. And so Monte Carlo Markov chains are your friend there. The Monte Carlo part is Monte Carlo casinos. It's the random, it's trying things many, many times and see if you get lucky. And then the Markov chains is the random walk component to it. Not just randomly sample, just jump around like a crazy person, but actually use the previous information to inform your next step. So it's not completely random, it's random with some logic. And so that's why it's got its own new name now. And so this is a very powerful and useful technique for you to use if you have a complex model, if your data is not completely covering everything, and if you're starting to suspect that the whole thing might not, your inferred models may not have Gaussian uncertainties associated with them, and you want to compare different models to each other. So these are all good, good complex ways to if you have complex data and complex models, you can compare them more easily to each other, and you can report your uncertainties with more honesty, I would say. So I'm a big fan of MCMC. It's not the great Thor's hammer of all your problems, but it does certainly has its usage beyond what we've been doing so far. So it's kind of a logical progression from bootstrapping and jackknifing and sampling doing a chi-square fit. All right. So as we progress, here's MCMC.